La la la. Sure. All right. I'll begin with a word of prayer here once I finish getting the quizzes. Thank you. Thank you, thank you. All right. So I'll begin. Dearly Father, we thank you for this day. Again, I thank you for these students. Just ask you'd be glorified in what we do this day. We just pray. Let's pray that the students would understand and that they would ask good questions as they think of them, Lord. In your name I pray, Lord Jesus. Amen. All right, so I guess I'm supposed to top hat, right? So, find that. Hey, good news. I'm teaching 2 sections of college algebra next semester, so, well, that's irrelevant to you guys, right? I hope that's irrelevant to you guys. 83.99. It better be irrelevant to you guys. I'm not a big fan of recycling in classes. I want to see you do. I want to see you one and done if possible. Now, for some of you, it's too late. I know it's already not your first time in the college algebra, but let us be optimistic that this is the last time, all right? Okay, so let me just run through the solution to the quiz right quick for you guys, because it's kind of a natural jumping off point for what we're doing today. Now, problem 1, I heard one of you say that this is boring. I like the sound of that. If you think this problem is boring, that is wonderful. But I hope you say that from a perspective of understanding it and not just a commentary on the subject matter of this course. Let's see here. So this x squared plus 6x plus 10, can be factored? I don't think so because, yeah, it's prime, right? If we complete the square on this thing, it's x plus 3 squared plus 1, so it shows that this is prime, right? Now, if you didn't do that and you just said, well, it can't be factored, that's also fine. I wouldn't charge you anything for that. This here is x squared minus 9 times x squared plus 9 by the difference of squares, right? But we're not quite done yet because this will factor as well. So what we got is x plus 3 squared plus 1 times x plus 3 times x minus 3 times x squared plus 9. And there you go. That was the answer to problem number 1. Right? Yep.
So because x squared plus 6 plus 10 is 12, can we leave it like that in the future? Or, okay.
Yeah, we could. You didn't have to. This could also have been x squared plus 6x plus 10. That would have also been a totally legitimate answer here. Sure. If that's what some of you were asking that. Questions? No? So this is important, right? Because if I had followed this up with the question graph y equals f of x, you would have needed to be able to do this factoring to graph it, right?
Right.
So there's that. Also, this is a pretty standard factoring question that you might see on the final, which will be not too long from now, right? Problem 2. I have y is equal to x plus 3 times x minus 2 squared. Now this one, I already factored it for you, right? Yes, sir?
Is the final going to be cumulative?
Yeah, the final's cumulative. It's just complete the square. It's like all completing the square.
Oh, really?
No. I just
It should be completing the square and linear equations.
completing the square in linear equations. No, and linear equations. Okay, yeah. Okay, so what you do here is make a number line. Our critical numbers are what? -3 and 2. Very good. So I put my -3 here. I put my 2 here. And we plug in some points, right? Like plug in 0, what do you get? You get 3 times -2 squared, which is 12, right? So it's positive where there's 0. Now that's between your critical numbers, right? So the sign chart, it's pluses up in here, and then this is odd. It's a linear power, so it's going to flip to minus over here. It doesn't flip after the 2, right? This minus 2 squared, and you can check this if you don't believe me. Try plugging in 4. You get 7 times 2 squared, which is, still positive. So it's still plus over here. What that means is that the graph bounces. So the graph's bouncing at 2, basically. So the sketch of this polynomial should look something like, so you've got zeros at 2 and also at -3. And it's negative, right? Where's this x-intercept? Oh yeah, 12, we said that. So that looks like this on my graph because it's not to scale, right? And then what happens is it comes back down here and it bounces. So roughly speaking, there you go. This is y equals x plus 3 times x minus 2 squared. Now, usually when I ask you guys to sketch a graph, I give you some kind of template graph paper on the quiz to write things over. I'm sorry I didn't do that today. I was just a little bit crunched for time today. So, you forgive me? Thank you. See, the thing is, my Calculus 2 class has this giant. Do you think your homework is long? You have no idea. You should see my Calculus 2 homework. You guys have it made. And so, Calculus 2 students are coming to ask me about their homework this week, which is why my office hours are a little bit full. What was the question?
How did you get the y-intercept?
The y-intercept I got from plugging in 0. Plug in x equals to 0. We get y is equal to 3 times minus 2 squared, which is equal to 12. So 0, 12. That right there is the y-intercept. Now, it's not, this obviously is not to scale, right? Because this is 3, this is 2. Yeah? How many turning points does this graph have? I saw 2. That's right. Notice that one of the turning points is also the x-intercept, right? So when you have a factor squared, you get a bounce, right? A bounce off the axis is a turning point on the axis. All right. Fun fact, if you have an nth order polynomial, you're not going to have more than n minus 1 turning points. Like a quadratic only has 1 turning point. A cubic can have at most 2. It doesn't have to have 2, though. It may or may not. All right, so next up here we've got y is equal to x squared minus 16 squared. So what we're looking at here is x minus 4 times x plus 4 squared, which is x minus 4 squared times x plus 4 squared. And so the critical numbers are minus 4 and 4, and the sign chart is actually kind of boring. Well, is it? Yeah, I think the sign chart's kind of boring, isn't it? Because it's just what? Yeah, it's just always positive, right? So what's the deal with the graph here? How's that work? It's just bounces. Yeah, it's got a bounce at 4, minus 4. It's got a bounce at 4, right? And its y-intercept is huge. It's if you plug in x equal to 0, you get minus 16 squared, which is I think 256. So the y-intercept is ginormous, but I'll draw it like it's here. And so this has to do something like this. It's got to turn around somewhere. It's got to come back down. It's got to bounce again. So something like that. So minus 4 and 4, roughly speaking, that's the graph. So you notice these heuristic pictures that I make, I really don't care about making the scale the same on the x and the y-axis. All right? But that's it. Any questions? Cheyenne, I think you had a question about a homework problem. I can talk about that one. Problem 65. Yeah, thanks. Muchas gracias. F of 0 is 32. And you're supposed to find the polynomial of least degree, right? Now the graph that you're given, I'll try to reproduce it here. It's like this, and then it comes back down, and then it bounces again. So you're given this graph. And you can look at the graph and see that the bouncing point is -6, and it crosses at -2, and it bounces over here at 4. All right, and we're supposed to find the polynomial of least degree. It looks like that. How should we do this? So you guys help me do your homework together. F of x is equal to what? So when you're doing this kind of problem, to start with, just acknowledge that there can be a constant out front. We don't know what the constant is a priori, like before the fact, but I'll just put an a there. We don't know what that is. All right? Then what would you guys tell me? How can I make it bounce at -6? What do I need in the formula? A square of what? 6, right? X plus 6. So I put x plus 6. That is that's the necessary thing to get it to bounce at -6, right? To get it to cross at -2, what do we want? X plus 2. And so you could also have x plus 2 cubed, right? You could also have x plus 6 to the 4th power. It would also make it bounce and cross. But then it would not be what? The polynomial of least degree. You have one job. Golly.
Don't break that promise.
You better not. It's irreplaceable.
That's your pride and joy.
I wish I was joking, but I'm actually not. Like, I tried to, like, IT has that same model. I mean, it says Canon RX F5, whatever the serial number is. You can get it from I can get it from IT, borrow it for the day, and then I go into it. It's got a completely different menu structure, which doesn't allow me to like choose the focal length manually. It's more smartphone-esque, the new ones. It's got the same stupid model number, right? So if I go to try to replace this, I'm going to be faced with the problem of trying to buy a camera with the same model number that's different than the ones that are like that's from like 10 years ago, right? So they've gotten stupider. So I'm not sure exactly how much money I have to spend to replace that camera, but my feeling is like $2,000. I'm not sure exactly because, you know, these companies, they tend to like give you less and less buttons and pick it more and more like menu based, and so it's just, anyway, I digress.
Anything for the subscribers, right?
Yeah, I mean, yeah, oh yes, like and please subscribe. For a while, calculus was like, my classes were trying to get me to say this at like the start and end of classes. Like, it wasn't my idea to start a YouTube channel. The students were like, you should start a YouTube channel. I'm like, what's that? And so they helped me start it, and I just started putting videos there. They used to hold up a piece of paper at the end that said like and please subscribe. If you look at some of the early videos, you should do that. Yeah, I should monetize my channels. I could make tens of. I should have merch. I'm thinking like I should have this blue shirt, but it should say cook. It should say cook on the back, right? Yeah, that's what I want.
Your face in the front would be awesome too.
So if I had merch, you'd buy my merch?
Yes.
All right. Maybe I could make tens of hundreds of dollars.
To sell that shirt for like $100
So you're interested in purchasing like old cook shirts, like authentic. I have one I wrecked my bike on. It's got like the shirt tore out of the front. I'll sell that one to you for $1. What? Of course. It's the bike I ride from my office back to the parking garage because, you know, I was trying to avoid somebody on a sidewalk, and then I like bought it on the edge. I tried to like come back onto the thing, but it's like this far up. So then, of course, the bike stayed off the sidewalk, and I went onto the sidewalk, and in the process, I like ripped my shirt. I had
How many of those do you have?
I don't know, I really don't know. I really don't know, like many.
Can you make a YouTube video counting?
Let's see here. I feel like this is not helping you with your homework. Let me go on here. X minus 4 squared, right? So will that make the graph happen?
Yes.
I think that's everything, right? We got the bounce at -6. We got the crossing at -2. We've got a bounce at 4. And you see there's still some flexibility left, see, because you can put any number you want here and have those features, right? In fact, if you make a negative, it would do what? It would basically the same picture, but turn it over, you know? Yep.
You mean to put a number to get full points in our homework?
Yes. So we also have another piece of data we haven't used yet, which is what?
So
F of 0. Yeah, if we plug in 0, it should be equal to 32. Right, this. So f of 0 is 32. But what else is it equal to? It's equal to a times what? 6 squared times 2 times -4 squared. So solve for a, and your homework problem is done. Yeah, a is what? 32 divided by, you know, what's this? 36 times,
Wait, where did you get the 32 from?
times
0.
Oh, come on, I got it.
32? 2 times 16 is 32, right?
Yeah.
So that you've got 36 times 32 on the right-hand side. And so you see what the answer is. I mean, the a is what? 1 over 36. So what's the answer? The answer is f of x is 1 over 36.
1,000.
What happened?
Oh, I
Something like that. Yes?
How did you get like x plus 6 squared?
Because it bounces. So the reason, what's the difference between -6 and 4 is it bounces at -6 and 4, but it doesn't at 2, at -2, right? That's the difference. So in fact, if you understand this problem, you're really a long ways to where you need to be in terms of polynomial graphing. This problem is like in reverse, right? Like on your quiz, I gave you a formula and said sketch the graph, right? This is the other kind of problem. I give you the graph and I say find the formula. But it's understanding the same thing, right? It's 2 different ways to ask the same question. It's just 2 different ways to skin a cat, right? Either way. What? Yes?
I do have a question about the top hat. About the top hat. This is not mandatory, right? Because
Well,
I'm way behind on my top hat.
oh, your top hat doesn't matter, but what matters is the...
It would reflect very badly on my
Oh, yeah, you don't worry about your top hat. Where's my paper? My paper of remembrance. Aw, man. Well, I have your quizzes here, so I know that you're here, you know. And I seem to not have the attendance sheet. My office is a little bit askew at the moment, and so I'm sorry. I don't have an attendance sheet for you to sign. You'll forgive me, hopefully. What's that?
Next class.
Yeah, next class you can sign double. All right, so I do have your quiz, so I can tell who's here. But all right, so let's move on. The next topic is graphing rational functions. How do you do that? How do you think we're going to graph rational functions? What is a rational function? I think we've talked about this before, but let me remind you. That means that f of x is equal to like p of x divided by q of x, where p and q are polynomials, right? So it's a fraction of polynomials. Now, generically speaking, this is equal to something like g of x plus r of x over q of x, where the degree of r of x is strictly less than the degree of q of x. All right? How do you find this mysterious g for a given problem? Well, that's what long division does for you. All right, so this kind of function right here, this is called, what I call this a proper rational function. And my language is, I'm trying to reflect like the same idea we have about fractions, right? Like if you have, 40 over 13, that's an improper fraction, right? So 40 over 13 you can rewrite as 3 plus 1 over 13, right? That's a mixed fraction. But 1 over 13 is a proper fraction, right? Because the numerator is smaller than the denominator. Now, proper rational functions are in some sense really easy to graph because a proper rational function has graph which goes to 0 as y goes to, say, plus or minus infinity. So if you want to graph a proper rational function, the way it behaves really far out, it's very simple. So let me look at some simple examples here. So for example, if I was to graph y equals, 1 over x minus 1, for instance. The way this is graphed is pretty simple. What you want to do is acknowledge that there is a division by 0 here, right? So what is that? What happens then? Where you have division by 0, we have what's called the vertical asymptote. So, but you can make a sign chart. There's only one critical number here, it's 1. So you got plus to the right of 1, you got minus to the left of 1. The graph then looks something like this. We have a vertical asymptote at 1. All right. And what's its y-intercept? Plug in 0, what do you get? If we think, let's call this thing f of x to give it a name, all right? What is f of 0? 1 over 0 minus 1, which is what? 1 over minus 1, which is just negative 1. So the y-intercept here is just negative 1. And so these are pretty easy to graph, like a proper rational function. It has to blow up at the y-intercept, at the vertical asymptotes, all right? And it has to also tend to 0 as you go really far out either way, all right? Like that. So there you go. We graphed a rational function. This is kind of the most basic, interesting one. Example 2. What if we're going to graph y equals to, I don't know, x over x squared minus 4. Let's graph this thing. Again, this is a proper rational function, so like the horizontal asymptotes are just the x-axis going both ways. It gets drawn into 0 eventually, all right? Now, can you factor the denominator? We can, right? What is it? It's x plus 2, x minus 2. Now that's important. So with polynomials, we're just looking for where the polynomial is 0, right? For a rational function, we're looking for where either the numerator is 0 or the denominator is 0. Both of those give us what are called critical numbers. So here we have critical numbers 0, minus 2, and 2. The critical numbers that are from the numerator are very different than the critical numbers from the denominator, right? What does it mean if you have a 0 in the numerator of a fraction? The fraction's just 0, right? But if you have a 0 in the denominator of a fraction, that's undefined. So places where you have a 0 in the denominator are places where your graph has a vertical asymptote. In contrast, the zeros in the numerator just give you, well, x-intercepts. Now this is the simplest possible discussion, but it turns out there's some complications that I'll have to get to. Things called holes in the graph. We'll have to talk about that. But first things first here, simple example. Well, I don't know if this example is maybe simple is a little bit too strong a description, but it's not as complicated as some of the other things we'll run into. So that's my sign chart. I put my critical numbers. All right. The only place that the graph can change from positive to negative is either when it crosses the x-axis at a 0 or when it's got a vertical asymptote. See, vertical asymptote allows you to jump from one side, from positive to negative, even though you haven't actually cut through the axis. See that? Like here, we switched from positive to negative, even though we didn't cross the x-axis, because there's this discontinuity in the graph, right? Now, my brother, he teaches that it just goes to infinity, and they join at infinity, but I don't feel like that's something I should be telling college algebra, so I don't. So disregard my previous comment.
Will they just go opposite directions forever?
We just put the same infinity at above and below. Just join them.
I see how I do.
That's it, exactly, yes, yes. Yeah, I don't know. But my brother has a way of lying about things forcefully in such a way that they make sense. It's kind of a used car salesman sometimes with mathematics, but it works. It works for him, but I don't believe in his lies, so it doesn't work for me. So something like that. Okay, so those are your vertical asymptotes. One at -2 and one at 2, right? Where's the x-intercept? It's actually at the, yeah, it's at 0. In fact, it's at the origin, right? The x-intercept here is the origin. And so what's my graph look like? Remember, proper rational function has a graph which goes to 0 as y goes to plus or minus infinity. So, oh, I'm sorry, I need to test my points. My bad. You guys, help me out. What happens if I plug in, plug in 3. Good idea. 3, 3 over 9, so 3/5, right? The larger point is it's positive. Now, the sign flip theorem still works here. All right, so like I look at it, -2, x minus 2 appears once, so we flip signs. X just appears once, so we flip signs. Minus this x plus 2 just appears once, so we flip signs again. And so that's what it looks like, the sign chart. And then, okay, so it has to look then like this. The graph goes down like so. And then it's positive, infinity, and then it goes through 0, and then it goes down here, down, down, down. And then it flips back up here like so, like that. So there you go. That's the graph of y equals f of x. Once you can draw a graph like this, you can answer other questions, like what's the domain and what's the range of this function? Can you tell me? Yeah.
-2, meaning -2 to +2 with the not
So minus infinity to 2, -2, union -2 to 2, union 2 to infinity. So the range is, excuse me, the domain, it's kind of a pain, right? What's the range? Right, yeah, the range is everything. You see that? The range for this one is everything because it keeps going and all y values are covered. What's the range from example 1? Right, so the range here is everything except for 0, right? Because there's no point in that graph where you hit the x-axis. You never get to y equals to 0. You get arbitrarily close to it, but you never get there. So. All right, let's look at some more examples if I can find my eraser. Do, 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 do. You got this all on videotape? Okay. You know, there's this, back in the day, we had this thing called videotape. I know, it's kind of... You used to have this giant plastic cassette which would hold 6 whole hours of video. It was amazing. Oh yes, please be kind, rewind. Yes, oh, now you're taking me back. Let's see here. You used to go and go to this place called the video store and then stare at the videos and try to decide which one to rent. Yeah. Now you guys just binge stuff. You still have a VHS player that works? Ah. I don't think I do. I don't think I do. I had a whole box of VHS tapes, and I went to go watch them, and they'd gotten like a mold in them, so they wouldn't play anymore, and it was so sad. So, it's Mystery Science Theater 3000. I had dozens and dozens of episodes recorded. They were all trash. Oh well. I mean, once upon a time, there was actually programming on Comedy Central which wasn't completely reprehensible. If you go back far enough, but you have to go really far back, I think. I don't know. I don't have cable, so I don't know. But all right. Uh-oh. Huh. That's interesting. Let's see here. Example 3. So let's see here. Let's look at one that's not proper. So suppose you have something like f of x is equal to x minus 2 over, let's say, x plus 3. And you want to graph this one. All right? So, I mean, you can do it, but you have to be, let's see here, how to explain this. What happens when x gets really, really big? See, this is not a proper rational function because the degree of the top and the degree of the bottom are they're both equal to 1, right? So, but we can still make our sign chart, right? What are the critical numbers? 2 and minus 3. Very good. So here we go. Minus 3 comes first. 2 comes over here. What happens when you plug in 0? Negative 2/3, right? So 0 is negative. So it's negative in this case. And if I plug in 3, what happens? I get 1 over 4. It's positive over here, right? Of course, there's, the sign flips, and it's going to flip over here as well. So it's positive over here. So the thing is, in the previous 2 examples I've done, the horizontal asymptote of those graphs was y equals to 0. This one is not the case. Let me just show you some numerical evidence. Like, try plugging in, what's f of 100? What do you got? 100 minus 2 over 100 plus 3, right? So that's 98 over 103. What's f of minus 100? Minus 100 minus 2 over minus 100 plus 3. So you got what? Right? So approximately, what are those equal to? You don't really need a calculator for this, right? What's that? It's almost 1. And the bottom one? But the minuses cancel, right? So It's also 1, right? Yeah. So actually, it's just a little less than 1, and this one's just a little bit bigger than 1, right? What happens if you go to 1,000,000? Same story, right? But you're even closer to 1. So what this tells me is that this graph has a horizontal asymptote of y equals to 1. Horizontal asymptote of y equals to 1. So because it doesn't give me great joy to write out horizontal asymptote, let us agree that we will refer to this as ha, if that's okay with you guys. In contrast, what does this problem also have? It has a vertical asymptote, which we will refer to as VA, of x equal to minus 3, right? There's a vertical asymptote there, and there's a horizontal asymptote there. Now, horizontal asymptotes, in principle, you can cross. Vertical asymptotes, you can't cross with these kind of functions. So the horizontal asymptote, the vertical asymptote's at minus 3, right? So here. And the horizontal asymptote's y equals to 1, so let me draw it right here. And these kind of frame where the graph goes, all right? And what did we observe? We observed that, and what else do I have? It's got a 0 where this 2 is making the numerator 0, right? So we have an x-intercept there at 2, all right? So, and, all right, so what's the graph look like? What did we say? When we plug in 100, it's a number of what? Just a little less than 1, right? So if you look at that, what's going to happen, and let's see here, where does it cross the x-axis? Yeah, at 2, and also where? In some sense, this vertical asymptote, it jumps on the other side, right? So, but it actually crosses it at 2, right? So this is, and our y-intercept was what, minus 2/3? So something like that. We calculated that before. So the graph looks something like this. And then over here, you're up here like that. So I haven't done it quite. I mean, this shape isn't quite right, but it's roughly this. This is y equals x minus 2 over x plus 3. Now, so I just plugged in numbers for you to see the horizontal asymptote. Can anybody tell me another way we could have seen it? Let me show you another way of thinking about this example. Another way to think about this one. What if we did long division or something like that? What if you divide x plus 3 into x minus 2? How does that go? How many times can you put x plus 3 into x minus 2? Just once, right? So I put a 1 here. That puts x plus 3 down here. I subtract. The x's cancel. We get minus 5. And so what that shows me is that f of x can be rewritten as 1 minus 5 over x plus 3. So what you're looking at, if you want to think about it this way, is the graph of the reciprocal function multiplied by minus 5. What that does is it flips the reciprocal function over and stretches it out, and then you shift it up 1. And that's the graph. So like, you can think about it in terms of transformations of graph. The reciprocal graph looks like this, right? And then if you shift 3 to the left, it looks like that. And then if you multiply by minus 5, it looks like this. And then if you shift it up 1, you get to where we got to. So, sorry, the contrast of blue on blue is not great, but Something I said? I don't know. Let's see here. Yeah, class not over. Hey, not cool. I'm just kidding. If you guys need to go somewhere, I understand. You can watch the video later. It's all good. It's all good. Just do your homework. That's the main thing for me. You know, do your homework. Please do your homework. Okay, so does this make sense? Do you see the difference? The difference between this example and the first two is mainly that it's not a proper rational function, so we can get an interesting horizontal asymptote of 1 instead of 0. All right. Look at another example. Example 4. Let's look at f of x equal to x squared plus 3x plus 2 divided by x cubed minus x plus x. There. So something new is going to happen in this one, all right? The good news is it's a proper rational function, right? We have degree 3 on the bottom. We have degree 2 on the top. So what's the horizontal asymptotes? It's going to go to 0 eventually, right? Because if you think about plugging big numbers into this formula, the denominator wins. Think about this. If you plug 1,000 into this, you get 1 billion from this x cubed term. Everything else is minuscule in comparison. And the same thing happens for like minus 1,000. You get minus 1 billion, you know? So this definitely is going to 0 for sufficiently large values. Like you can get as close to 0 as you want. That's the fate of this function, in either direction if you go far away from the y-axis. But interesting things happen closer to the y-axis. Let's see what happens. So we can factor. How does that go? X plus 1? Yeah, x plus 1. You say x plus 1 times x plus 2. How about the denominator? Aw, man. All right, I'm going to have to invoke my right as professor to so this is, you know, once you get a PhD in math, you're allowed to change the problems afterwards. So there we go. So that's what I wanted. You are not allowed to do that on the test, no. Change every problem to 2 plus 2. So if I make that, if I put that x squared there, I can factor x squared out, right? So, and what am I left with? Just x plus 1 actually, right?
Oh, you changed
Yeah, I changed it. The x plus 1s cancel out. When do they cancel out? So this is, you're right, this is equal to x plus 2 over x squared when x is not equal to minus 1. Right? Totally agree. You're right. You can do that. Provided what? Provided x is not equal to minus 1. What's the domain of f of x? You're looking for x such that x is not equal to 0 and x is not equal to minus 1, right? In other words, 0 and minus 1 are not in the domain of this function. Okay? Question. If I make g of x, let me just change the letter a little bit. If I look at g of x equal to x plus 2 over x squared like this, right? What's the domain of g of x? Right, so 0 is the one thing we can't put into G. Everything else is copacetic, right? I mean, it's fine. So it's just x such that x is not equal to 0. See, so my point to you is that the domain of the purple is bigger than the domain of the blue formula, right? By canceling out that x plus 1, we have added another point into the domain which wasn't there before. So how do you, but our problem was to graph the given function, right? So how do we do it? What are the critical numbers? Yeah, yeah, -2, -1, 0, right? Isn't that it? That's where we either have 0 in the numerator or the denominator, right? The new feature of this example is what? Is that -1 is a 0 of both the numerator and the denominator, right? So let's make a sign chart here. And here we go. All right, so what do I got? What am I up against here? -2, -1, 0. And so if we plug in, the fun thing is we can actually use this thing over here. So by the way, this has a name. This is called the reduced function. So I oftentimes will say f reduced of x is equal to g of x. And this is the reduced function. And you could use that to figure out the sign other places, right? Like if I plug in 0, what do I get? Oh, I can't plug in 0. Wait a minute, don't do that. Plug in 1. Plug in 1, what do we get? 3 divided by 1 of 3, right? So it's positive at 1. So it's plus up in here. At 0, it has even order, right? So we don't change sign there, so we stay positive here. At -1, well, what happens at -1? See, if you look at the reduced function, nothing happens at -1, right? If you look back at this right here, what's the deal with -1? You have 1x plus 1 upstairs. You have 1x plus 1 downstairs. You have 2 of them, which means it has even order. So you don't change signs at -1. Of course, if you don't believe me, try plugging in -1.5 into the formula, see what happens. All right? If you plug in -1.5 into the formula, you'll get a positive number. And then what happens? -2, we flip back to minus again here. All right? So let's graph this thing. Where are my vertical asymptotes? Well, annoyingly, one of the vertical asymptotes is the y-axis, right? Like x equals to 0 is a vertical asymptote here, so I'll just kind of put it here. X equals to 0 is my one vertical asymptote. What else is going on? We have a 0 at -2, right? Anything else of interest? -1. What's the deal with -1? What is f reduced of -1 equal to? -1 plus 2 over -1 squared, right? What's that equal to? 1 over 1, right? Which is equal to 1. So the reduced function, its graph has value what? It has value 1 at -1. What this means is a kind of silly thing, but this means that there is a hole in the graph at -1, 1 for this function. Yep, hole in the graph. And I couldn't make it up. Are you disgusted by this? Yeah, it's crazy. So it has to do something like this. It turns around, it comes in here, here's a hole, and then it goes up like that. I'm sorry, for reasons of scaling, let me draw it lower so it looks better. It's bothering me. So, these wrinkles shouldn't be there. There's a hole in the graph here somewhere. I know where it is. It's at minus 1, 1. And then this is a volcano, like that. So I call this a volcano anyway. So the graph looks something like this. So have you guys seen a hole in the graph before?
Yeah.
You have? No? Check this out. Suppose I have x, I have y. I have y equals f of x, right? It looks like this. Whee! All right? Suppose I want to put a hole in the graph at some point, right? Suppose I want to put a hole in the graph right here. So that would be, let's say, I don't know, at 4. What function could have the same graph as f, but has a hole at 4? It's very silly, but simple. What you do is you just write this, y equals f of x times something. And the something, you put in these parentheses, you want it to always be 1 when x is not equal to 4, and you want it to be undefined when x equals to 4. It's kind of like a mathematical hole punch. And so all you do is you just multiply by x minus 4 over x minus 4. And so that silly factor, it's always 1, except at 4 where it's undefined. And so what that does is it takes the graph of f of x and it just puts a hole at 4. So in some sense, these are very silly, but it happens in formulas that we have whenever we have the same factor above and below. So we just have to be aware of it, all right? But anyway, those are the main points. So have a good weekend. Wait a minute, weekend.
You have a good weekend too, Tuesday.
We still have class Thursday, right? Yeah. Yeah. It is Thursday. Don't do that to me.
We told everyone to quit subscribe.
You're up to no good.
I have a lot of fun
Did you stop it? Oh, no.
No.